We're presenting an ongoing series of lectures regarding marine magnetometers and their application. Today we're going to talk about targets and how far we can see a certain target and how that informs us about what our lane spacing should be for the actual survey. We have a rule of thumb regarding the distance at which we can see an object. These rules are based on induced magnetics only, and so I'm going to define what induced magnetism is and what these numbers mean in terms of depth and mass of the target we're looking for. So there are two types of magnetism. One is called induced and the other is called remnant or permanent. The induced magnetics means that we have a magnet. This is something we've all done in grade school. We have a paper clip and we have a pin. If we hold the magnet close to the paper clip, we can induce a magnetic field in it, and the pin will attach itself to the paper clip. When we remove the magnet, the pin will fall down. So we are inducing a magnetic field in a material, the paper clip, which has a property called susceptibility. We use that an estimate of an object's susceptibility to determine how far away we can see it. So this is induced. Then we also have remnant or permanent magnetism. Remnant or permanent magnetism means that we have a magnet and we have a paper clip and we stroke the paper clip on the magnet and it becomes its own magnet. So now we have permanently magnetized the paper clip. So it becomes a magnet all of its own, and even if we pull the magnet away, a pin will still be attracted to the paper clip. It now has permanent or remnant magnetism. Most of our targets that we are looking for in search, in marine magnetic search, have this property of both induced and remnant fields, remnant or permanent fields. And by these types of targets, I mean unexploded ordnance, pipelines, tools, telecommunication cables, other sorts of shipwrecks. They all have this type of property. The next term we want to talk about is susceptibility. And susceptibility simply means how susceptible is this paperclip to being magnetized. So it's a property of the steel, if you will. It's a property of the material in that items with high susceptibility are more easily magnetized or pick up a magnetic field. Therefore, they distort the Earth's magnetic field more, and we can see them easier with the magnetometer. So the rule of thumb that we use in determining the size of targets and therefore the distance to which we can see them is that 1 ton equals 1 nanotesla at 100 feet. Now 1 nanotesla, there are 100,000 nanoteslas equals 1 Gauss. And 1 Gauss is basically the strength of the Earth's magnetic field. So when we look at the Earth, and we know that it has a North Pole and a South Pole, and the field lines are vertical at the pole and horizontal at the equator, the field varies from about 0.7 Gauss in the northern hemispheres down to about 0.2 Gauss in certain places off of Brazil. We know somewhat why these magnetic fields are created, how they're created, but not exactly. And so there is some odd shapes to the way in which the Earth's magnetic field shows itself. When we say 1 nanotesla, we mean a 1 nanotesla distortion of the Earth's field. because here in San Francisco, the Earth's field is coming in from the south. These are the Earth field vector. It's coming in from the south, or we can call them the flux lines, at about 60 degrees. So if we were to, here we are in San Francisco, and the Earth flux lines are coming in from the south at about 60 degrees. When we have an object, either above the ground or below the ground, or remembering that water and Earth in general, when we're looking for targets, these materials of sand and water are invisible. When we have the Earth's flux lines coming through these materials, and then they come upon a target, since these targets are distorting the Earth's magnetic field, we get these flux lines coming together and expanding. And that's what the magnetometer actually reads. So if we have normal flux lines in the northern hemisphere in San Francisco of this angle, and then we have an object which has susceptibility, of approximately 10 units, let us say. 10 units means how much it distorts the Earth's field. And we use 10 units as 10 CGS units as a sort of a ballpark number for a variety of targets, such as soft steels. Then what happens is that the Earth's flux lines actually tend to dip into this object. So we get a distortion at quite some distance. And when we bring our magnetometer, be it a land-based or marine-based magnetometer, through this field, remembering that this is the south and this is the north, right? The field is coming in from the south to the north. What we see is we see a compression of the flux lines to the south and an expansion of them to the north. So if we actually look at the flux lines, they're coming in here, and then on the other side, where this field is bucking the Earth's field, out here we actually get the field expanded. The flux lines are expanded, and then they return to their normal flux density. And so when we take a sensor and we move it through the Earth's field from the south to the north, we will get a high to the south, and then we will go through zero, and we will get a low to the north, and then we come back to zero. And where the object is located is at the inflection point, which is midway between the high and the low, and essentially at the greatest slope between these high and low fields. So that's where the object is, and we can tell something about the object by the distance between the amplitudes and the distance of the or the wavelength of the anomaly that we have measured.